All right, so now I'm going to record the second video. So last time, remember we discussed the magnetic field and also how do we define magnetic field. Well, it's hard to define magnetic field using magnets because we don't have, there's no isolated north or south pole. But we can define magnetic field using electric charge. Because it turns out that the magnetic field also has a force on the electric charge if the charge is moving the magnetic field, okay? And then this is the theory we learned. If you want to find out the magnetic force on the electric charge moving that magnetic field, use this theory, right? There's a cross product here, V crosses B, so that this, the magnitude of the force is going to be this, right? So, because the definition of the cross product, the magnitude is always the product of these two magnitudes and then sine theta. And then there's also the charge here, so make the charge positive. So that's how you find the magnitude of the magnetic force, right? The direction, okay, it's very non-intuitive, right? So that's why we did a lot of practice last time. You're going to put your four fingers in the direction of V, the velocity of the moving charge, and then you're going to use your right hand, right, and use and then curl them into the direction of B. And then, as I said, there's always one unique way to do that. And then you're going to find out that your thumb, the thumb of your right hand is pointing into some direction. Then take a look at the sign of the charge, right? If the charge is positive, okay, the direction of your thumb is the direction of the force. If the charge is negative, it's going to be opposite to it. So it's going to flip your thumb. That's the direction of the magnetic force on that electric charge. Again, very non-intuitive, right? Very weird. That's because we don't have experience. We don't have direct experience with this magnetic field and then moving electric charge in the magnetic field, right? We never do that experiment in our life. But as I said, there is a way to test a theory, okay? And then we're going to do that in a little bit late, maybe next lecture, something like that. So, and then we did practice right-hand rule a lot because it's very non-intuitive. Now, today we're going to discuss the detail, discuss the motion of a moving electric charge in the magnetic field in detail. So in general, the motion of an electric charge in a magnetic field is very complicated, right? Because look at this equation. Okay, if there's a force on this moving charge, so it's going to definitely change its velocity. It's going to affect its velocity. So the force is going to affect the velocity. But the force is also depends on the velocity. So when the velocity changes, it's going to also act on this affect the force, okay? So everything's changing, right? So force is not going to be a constant. It's not even going to be in the same direction. So it's very complicated, right? So it's very complicated. It's more complicated than electric force. Because electric force is this, right? So even though the electric field can be complicated, but if you already know the detail of the electric field, the force is always going to be either in the direction of the field or opposite to the field, right? So at least you don't need to worry about the direction. The direction doesn't depend on the motion of this charge, right? It only depends on the charge in the electric field. But the force from a magnetic field on a moving electric charge, okay, there's so many variables here, so it depends on a lot of things. So in general, the motion of electric charge in the magnetic field is very complicated. But in this class, we're just going to only discuss the simplest case, which is the electric charge moving in a uniform magnetic field, right? Uniform field is the simplest field. The field strength is the same everywhere. The direction is the same, okay? So we always start with uniform magnetic field. And then the charge is moving in a direction perpendicular to the field, okay? So that's the simplest case. And this is also a very interesting case, as we're going to see, okay? So now, let's see. So if there is a magnetic field, uniform, right? Let's say into the page, crosses into the page, right? dots out of the page. So this is there's a magnetic field in this region into the page, totally uniform, right? The magnitude is the same everywhere, the direction is always into the page. Now say there's a positive charge, okay, in this moving in this region, okay? So say a positive charge, now the initial velocity is v to the right, okay? So now let's see how it's going to move, okay? Well, because it's moving in a magnetic field, so there must be a magnetic force on it, right, from this theory. What is the direction of the magnetic force on this positive charge moving to the right? So you're going to use right-hand rule, right? Put the 4 fingers of the right hand in direction V, and then you're going to curl them into the direction of B, okay? So we're on lecture 12. This is slide 1, okay? Sorry, I should have said that earlier. So lecture 12, slide 1. Now, and then you see V toward B, and then there's only one unique way to do that, right? So your thumb is up. What is the sign of the charge? Positive. So, okay, so the force is going to be up. I don't need to flip any direction. So that means at this point, this charge is going to be pulled up. So this is going to be the force. Okay, it's very interesting, right? Very non-intuitive, but this is what we found in nature, right? So then this guy, so the magnetic field is not going to let it move straight to the right. It's going to pull in that way, right? So this guy tries to move straight to the right, but it feels the force up, pulling it in that direction. So this guy is not going to move in that direction, right? So this guy is going to be pulled up a little bit. It's going to be deflected up a little bit. So the next second, so it's going to be moving that way, right? So the next second, it's going to be somewhere here. Okay? So it wants to move to the right, but it feels the force pulling it in that direction. Then what is the direction? So what's going to happen after this second? Right. Well, what is the direction of velocity at this point? Well, it's always going to be tangent, right? So at this point, it's already been pulled in that direction. So actually, the direction of the velocity is going to be in this direction, right? It's not moving to the right anymore because it's been pulled and up a little bit. Now, if this is V, as I said, right? So the force from the magnetic field depends on the V, right? So everything's changing, okay? So then the force is going to change direction as well, right? So now what is the direction of the force? Still right-hand rule. Put your 4 fingers, the 4 fingers of the right hand in the direction of V. Now it's in this direction, right? Now you're going to still curl them into the direction of B, magnetic field. How do you do that? Well, you're going to do this. So the force is going to be in that direction, not straight up. It has an angle. So, but it's still going to be perpendicular to both the V and the B, right? So that's how I'm going to draw this direction. Okay? So again, it cannot keep moving in that direction. It's going to be pulled in this direction as well. So next second, it's going to be pulled in that direction. Okay? Say it's here. It's already here. Now it's already pulled in this direction. Now at this point, the velocity is up. Okay? If the velocity is up, so what would be the direction of the force on it? Now you're going to still do right-hand rule, right? Put your 4 fingers in direction V, curl them into B, which is into the page. Now the force is going to be to the left. Okay? Now you can see the pattern. This guy is going to be moving in a circle, okay? And it's going to be a complete circle, okay, perfect circle, because the force is always going to be perpendicular to the velocity. So it's not going to change the magnitude of velocity. It's only going to change the direction of the velocity, okay? Because it doesn't do any work. If it doesn't do any work, the kinetic energy doesn't change, right? Conservation of energy, see that we're still using the laws and the theories we learn in physics 1. So the complete, so if you look at the slide 1, lecture 12, slide 1, so it's going to be moving in a perfect circle. And then if nothing changes, it's just going to keep moving in that circle, okay, always. Okay, so that's very interesting, right? So this guy is just going to be moving in a circle because the force is always going to be perpendicular to the velocity, so it always changes direction and never changes magnitude. So you can do the same thing if you replace this with a negative charge. So the negative charge is going to feel a force down, so it's going to be moving also in that circle. So anyway, it doesn't really matter if it's a positive or negative charge. You use right-hand rule, you're going to find out that it's always going to be moving in a circle, and it's not going to change the circle, right? Because everything is going to be constant. Magnetic field, uniform, so it's a constant. The v, because the force is always perpendicular to the velocity, so it changes direction, but it doesn't change the magnitude of velocity because it doesn't do work. So it's going to just keep moving in this circle. Okay? So it's very interesting, okay? But again, it's actually very simple. This is the simplest case, right? And that's the only case we're going to discuss. As I said, in general, the motion of an electric charge in a magnetic field is very complicated. But this case we discuss in this class, it's very easy. Always circle, perfect circle, okay? Because the force, the magnetic force, is always perpendicular to the velocity, and now you can see it's always pointing to the center. What is that force? If you still remember the theory we learned in Physics 1, that is a centrifugal force. Okay? So in this case, we can find some properties of this circle. So first of all, if I want to find the radius of the circle, as I said, it's just going to keep moving the circle. It's not going to change, okay? Then it's going to have a radius, and the radius is going to be a constant if nothing changes, right? So how do I find the radius? Now we're going to use the theory for circular motion and also this theory for the magnetic force, okay? So, and then that's what we see on slide 2, okay, lecture 12, slide 2. Let's set up these two forces. First of all, I know that there must be a centrifugal force in any circular motion, right? Anything moving in a circular motion, there must be always a centrifugal force. And then if you still remember what we said in Physics 1, centrifugal force is not a new type of force, right? You have to identify which force is the centrifugal force, or sometimes it's a combination of many forces to be the centrifugal force for an object moving in a circle. In this case, obviously, the magnetic force is the centrifugal force, right? So if you calculate the magnetic force using that theory, or if you use the theory for centrifugal force, you calculate these two numbers, they should be equal, right? So that's how we set it up. Now the magnetic force is the centrifugal force. So these two numbers you calculate, they must be the same, okay? What is the theory for the centrifugal force? If you still remember that, right? It's going to be m v squared over r, right? The mass times the centrifugal acceleration. This is centrifugal acceleration we learned in Physics 1. You see that it's still true, okay? It's still true. Now, okay, now I'm going to apply that theory in this case to find the expression for the magnetic force, and then I want to find the expression for the radius at the end. So that's our goal. So that's how you find the force, right? You're going to do charge, magnitude of velocity, magnitude of magnetic field, and then sign theory. Now let's do that. I'm going to put the charge here. Okay, I'm going to use all the symbols because I just want to find expression for the radius. V, B. Now what is the angle theta? You look at this definition, right? There are two vectors, V and B. The angle theta must be the angle between these two vectors. So what is the angle between V and B? Okay, B is into the page, so that direction is fixed. It's not changing. But V actually changes direction. Then what is the angle between the V and B? Well, even though V changes direction all the time, but the magnetic field is perpendicular to this plane, right? So it's going to be always perpendicular to the V, right? So it doesn't matter if V is in this direction or that direction. B is into the page, so it's always perpendicular to V. So the angle between V and B in this special case always 90. Right? That's why we say this is the simplest case, right? So everything is almost constant. Now sine 90 is 1, right? So you rearrange this equation, what do you get? So you will get Q, V, B, this is 1, M, V squared over R. You rearrange this equation, right? V is going to cancel 1 power of this guy, so you get QB equals M, V over R. Okay, if you want to find an expression for R, now that's easy. If I put M and V at the top together, right, what is going to be the expression for R? That's going to be M, V, Q, B, right? So I'm going to rewrite it, I'm going to write it here. Okay, and you can see that this is how we predicted the radius of this circular motion of an electric charge in a magnetic field, right? You just need these 4 numbers, you put them in, you can predict the radius of this circular motion, and just going to keep moving that circle. It's not going to change, okay? So, and this equation is something you need to know how to derive, okay? This equation is not going to be given. This is the fundamental theory, okay? Again, the goal in physics is to understand the theory, and then we will have a lot of conclusions from the theory, okay? This is the conclusion from this theory, right? And then how did we derive this R? Because in this case, the charge is moving in a perfect circle, it's in a circular motion, there must be a centrifugal force. Which force is the centrifugal force? Magnetic force is the centrifugal force, okay? Equal them, put the expressions in. This is the expression for the magnetic force. This is the expression for the centrifugal force, right? We learned that in physics 1. Then do the algebra, you will find this equation. Okay, so everything is going to be from this fundamental theory. Okay, so this is something you need to know how to derive. Okay, this equation is not going to be given on a test. Okay, so another thing we can find. We can derive is the period. We can also find an expression for the period. How do we find that expression? Well, remember, the R, the radius, if something is in a uniform circular motion, which is true here, right? So we can always define a thing called period as the time for this object to complete 1 full cycle, okay? And then how do we connect the velocity, the radius, and the period? So if you still remember that, we use the definition of velocity to find out the relation. So it's not a new theory, okay? Still, it's not a new theory. Because anything moving, if you want to find the velocity, what do? Well, you're going to do distance over time, right? And then, okay, this guy is moving in a circle. And a uniform circle, the speed is a constant, right? So that's why we can connect everything. Otherwise, if everything is changing, so then you cannot draw a general conclusion. Uniform circular motion, it's always complete the circle in 1 period, right? It's going to be constant. So what if we put the period down here, right? I still want to use this definition to find the V. You're going to do distance over time, right? Now you tell me that, okay, you're going to pick the period as the time you put in here. Then you're going to put the distance it travels in 1 period at the top, so that you're still doing distance over time, right? You're not changing any definition. We don't change this definition. That's why they're called definitions, right? They're universal. What is the distance it's going to travel in 1 period? Right, that's the circumference, right? What is the circumference of the circle, okay? Don't tell me you don't know the circumference of the circle, okay? So you see that that's going to be a special equation for uniform circular motion, right? Again, this is, I wouldn't say that you really need to remember this equation, right? If you understand the theory, we're still doing distance over time. Now we're just doing distance over time in a uniform circular motion. So that's why you're going to get the circumference divided by period, the distance divided by period, right? So now if you have this, then you can use this R equation we just derived and then find expression for the period, right? So first of all, you rearrange this equation, what do you get? You will get period is going to be equal to 2 pi R over V, right? And then put this expression of R in here, you will get 2 pi m V over Q B divided by V. Right? And then this V is just going to cancel this V at the top. So at the end, you will just get 2 pi m Q B. Right? So this is total algebra. Even if you don't know what these symbols are, right? You just do algebra with these symbols. At the end, you will find the period is going to be this. Okay? So let's list it here. So that's another conclusion. All right, so again, these two equations are not going to be given. I wouldn't recommend that you remember that. Physics is not about memorizing equations. Understand them. How did we get these two equations, right? You need to know how to derive them. And once you have derived these two equations, remember, if you see a problem with a moving charge in the magnetic field, it's always going to be these two equations, okay? You don't need to find a different theory to solve any problem, okay? It's always going to be these two equations. Why? Because it's always going to be moving in a circle. What do you want to do, right? The velocity doesn't change. So I'm not going to ask you the velocity at this time is 5 meters per second. What is the velocity at that time? Still 5 meters per second, right? You don't even need to use Newton's second law. You don't even need to use conservation of energy or other laws to make predictions, because it's going to be a constant, right? So all we need to know is that if I want to predict a radius or the period, or if I want to use the radius and period to find something I need on the right, okay? So remember, when you see, even though in general the motion of electric charge in the magnetic field is very complicated, but in this simplest case, it's always going to be moving in a circle. Okay, always in the circle. If nothing changes, it's not going to change. It's always the same circle. If it's the same circle, then it's always going to be the radius and the period. And these two guys, they're not going to change, right, for the same circle. So we're just going to be manipulating these two equations to find the answers we need, okay? So even though this theory is new, the magnetic force on the electric charge is new to us, but this motion, it's actually very easy. Uniform circular motion, right? It's going to have a radius and period. When I have a problem like that, it's always going to be these two equations. Don't use Newton's second law. Don't use conservation of energy. You don't even need to use these laws, okay? So it's actually very easy, this part. Very easy. Now let's just take a look at some problems to practice this theory. So slide 3, lecture 12, slide 3. Let's take a look at this question. A proton is moving in a circular orbit of radius 14 centimeters in a uniform 0.25 Tesla magnetic field. Find the speed of the proton. Okay, I want to find the speed of the proton. The proton is moving in the magnetic field in a circular orbit. It's always going to be these two equations. Okay, don't go to a different equation. Don't even go to use a different theory. Okay, but again, you need to know how to derive these two equations. But once you derive these two equations, go ahead and use them. So I want to find the velocity, the speed of the proton. It's got to be this equation, right? Because this equation doesn't even have the speed. So I will use this equation. Okay, so let's see. If I use that equation, I want to find V. First of all, rearrange that equation, right? If you rearrange that equation, you're going to get V equals R Q B over M. All right. Now, do we have all the numbers we need? Proton. Okay, so proton mass, the mass of proton, the charge of proton, they are constant. So you don't need to worry about these constant. So charge and mass, we know that. Radius is given. Magnitude of the magnetic field given. Okay, put numbers in. then you can find the speed. All right. So in this case, the radius 14 centimeters. Again, pause the video and then do the math yourself, and then see if you can get the same answer. Now the charge of a proton, that's going to be the fundamental charge, right, is a constant. Magnetic field, 0.25 Tesla. Okay, so that's now divided by the mass of the proton, that's a constant. Right, very small number. Okay, and then you put all these numbers in, you will find the speed. Right, so the answer is A. Okay, very simple. Okay, it's always about these two equations. Okay. Now let's take a look at the second question, slide 4, lecture 12, slide 4. Now, but in this part, as I said, we will have a combination of electric field and magnetic. That's why we reviewed electric field last time, and we also compare the difference between these two theories. Right. Now let's take a look at this question. So in this question, there are these two fields, right? The electric field and then magnetic field. So let's see what is going on here. An electron is accelerated from rest through a potential difference of 500 volts, okay? In the electric field, right? Because you see electric potential, there must be electric field. And then injected into a uniform magnetic field. Once in the magnetic field, it completes half a revolution in 2 nanoseconds. We want to find the radius of its orbit, okay? We want to find the radius of its orbit in the magnetic field. That's the equation, okay? You don't need to go to new theory, different theory. You don't need to use a different equation. This is the equation to find the radius of the electric charge in the magnetic field, okay? So if I have all the numbers, then I'm just going to plug numbers in, right? So let's see if I have all these numbers. So I want this, right? These 4 numbers. The mass of the, okay, these two guys you don't need to worry about. The mass and charge, electron, constant, okay? Then I will need the V and B, right? So how do I find the B, right? So let me draw it out here. So this is what happens, right? So it's going to first go through, so these are 2 parallel plates, right? So there must be the electric field here. The negative charge electron starts from this plate and then goes to that plate, and then it's going to enter a magnetic field into the page. Now this once it's in the magnetic field, it's going to be moving in a circle, always, in this class, right? So in this region, so what is the direction of the force on it? You're going to do, so at this point, it's moving to the right, V toward B, right? Your thumb is up, but this is a negative charge, so it's going to feel a force in this way. So it's going to be pulled this way, so it's going to be actually moving in a circle this way, not that way, right? Okay, so that's going to be the trajectory of this electron in the magnetic field, okay? But in the electric field, it still goes in a straight line, right? So the problem says that this is 0 volt, this is 500 volt. So apparently, what is the direction of the electric field between these 2 plates? Think about it, okay? So what did we learn? Do you still remember that? The electric field is always in the direction of decreasing potential. This is lower than that, right? So the electric field must be in this direction. So that's the electric field. The then what is the direction of the force, electric force on this electron? Electric field, you use this theory. Alright, forget about the right-hand rule. Electric field in this direction, negative charge, so it's going to feel a force in the opposite direction. So this is going to be the direction of electric field force. And then the direction is not going to change, right? The magnitude is not going to change either because this is uniform electric field. Now it's just going to move in a straight line, okay? And it's going to be accelerating in the electric field, right? So that's why it's going to gain some speed at the end, and then it's going to enter the magnetic field. But once it's in the magnetic field, the velocity doesn't change, right? Well, the direction changes, but the speed doesn't change, right? Whatever the speed of this electron at this point, it's just going to carry the same speed, but it's just going to move in a circle, okay? So that's the difference between these two fields. Now, as I said, we don't need to worry about the mass and the charge because they are constant, right? Now, the magnetic field, say if I want to find the magnetic field, I just find the magnetic field in this region, right? I'm not going to find the magnetic field in that region because the magnetic field, that's the electric field. How do I find the magnetic field? Again, something moving, electric charge moving a magnetic field. It's got to be these two equations. You don't need to use a different theory. You don't need to find a new, another equation. We just use this equation. We want to use this theory to find radius, right? And now we're missing the magnetic field. Why don't we try the other equation? Because we only have two equations to find the B, right? So if I try this equation, to find the B, then I will rearrange this equation. So B is going to be 2 pi m divided by charge and the period. So if you have all these numbers, put them in, find the B, so it's going to be what we're going to use in this radius equation, right? Again, mass and charge, you don't need to worry about it. What about period? Now read this question carefully. It completes, once in the magnetic field, it completes half its revolution in 2 nanoseconds. Half a revolution in 2 nanoseconds. What is the period? 4 nanoseconds, right? So the period is going to be 4 nanoseconds. All right, so now put all the numbers in, you can find the B, right? Okay, do the algebra yourself, see if you can find the right answer. So you're going to do 2 pi, the mass of the electron, charge of the electron the same, right? And then you don't need to worry about the sign because everything is magnitude. And the period 4 nanoseconds. Okay, so that's how we find the B, right? This guy I found is going to be. Okay, it's a very small number, which makes sense. As I said, the magnetic field in real life, Tesla is a very large unit. If you get a magnetic field 1,000 Tesla, well, check your algebra, you may have made a mistake, okay? So that's going to be a use, right? But we're still missing V. Then you cannot find the V in this region because we have already used these two equations, right? We don't have another equation. We only have two equations in this magnetic field. And then also the V doesn't change, right? So you can't use anything else to connect this V because V is going to be a constant, right? If it's 5 meters per second, it's always 5 meters per second. So you can't find a V in this region. That's when you find a V using the electric field, right? Because the V doesn't change in the magnetic field. So whatever this velocity, the speed of the electron is, at this point, that's going to be the V in this magnetic field, right? Then how do I find the V in this region? Well, at this point, then you're going to use the theory we learned for electric field. Okay, so now we're going to move on to the electric field. So, okay, so that's what we did before, right? Forget about the magnetic field. Something, an electron moving in a magnetic field, and the magnetic field is No. Electron moving in an electric field. Electric field is uniform, right? Parallel plate. So how do you find the velocity? You can either do kinematics, you can do conservation of energy, right? In electric field, you still need to find a theory to help you figure things out, okay? In magnetic field, if an electric charge is moving, no, all about these two equations, okay? So now you can either, because the force is going to be a constant, the acceleration is going to be constant, right? So you can do either kinematics or conservation of energy, right? So let's do conservation of energy, okay? I'm running out of space, I'm going to erase these two guys. And also this guy. All right, so if I want to use conservation of energy, I would do this, right? Changing kinetic energy. Okay, in this case, only electric force on it, so nothing from the outside, so there's no external work. Well, let me write this complete equation. Okay, so the right-hand side is 0. Nothing's doing work from the outside. Now this guy, right, use the definition of kinetic energy. Now changing potential energy, remember this guy is related to the potential, right? So that's what we learn. Potential energy equals charge, test charge times the potential, right? So now in this case, we would have final potential minus initial potential. Okay? So now again, so the mass, this is an electron moving, so you're going to use the mass of electron, right? Initial speed, is it from a rest? Yeah, accelerated from rest. So initial velocity is 0. Now these two potentials are given in the problem, right? So this is going to be initial potential, 0 plugging, final potential 500 plugging. And notice that in this equation, there's no absolute value sign. So you don't drop these signs, okay? Always stick to the equations, okay? Otherwise, you're always getting actual negative sign. You don't know what to do, okay? Okay, again, do the algebra, see if you can find the speed, and then you can plug it into that equation, okay? Now I'm going to just finish the algebra. 1/2. Okay, initial velocity is 0. Now the charge is negative E, right? The final potential is 500 volts. Okay? Now this guy is going to be 0. Initial potential is 0, right? So, okay? And then you rearrange this equation. So this guy you don't need to worry about it. This guy you don't need to worry about it. You will get 1/2 mVf squared equals, move this term to the right, it becomes positive. You see that everything is going to work out. Now I can plug numbers in, find the V, right? Because you need the mass of the electron, the charge of the electron. So this final velocity I found is about okay, so that's going to be the velocity of the electron at this point, and then this electron is going to carry this velocity and then enter the magnetic field, and it's just going to be the same speed, right? So that's not going to change. Now we're ready to put numbers into this equation, right? The mass, the velocity, the charge, the magnetic field, okay? Now you can put all the numbers in. At the end, you will find the answer. Okay, do the algebra, see if you can find the right answer. All right, this is the B you plug in, and this is the V you plug in. Mass and charge constant. Okay, so you see that if the electric charge is moving in a magnetic field, okay, it's all about these two equations. I erased them, right? But it's all about these two equations. You don't need to find a theory to make predictions, okay? You don't need to use a different equation. So it's actually easy, okay? This part is actually easy, even though it's new to us, even though it's very non-intuitive to us. But this part is easy. And then if the electric charge is moving in an electric field, you still need to find a theory to help you figure things out, right? Because everything is still changing, okay? The velocity changing, the velocity can change, and then you're going to still do kinematics or conservation of energy, okay? So that's this question. Now, okay. Okay, so now I'm going to tell you some application of this that theory. Okay, so first application is this velocity selector, slide 5. Okay, what is a velocity selector? So in a lot of problems we solved. So the problem will say an electron has some velocity, a proton has some velocity. But in a real experiment, how do you make sure that these particles, they have the velocity you want, right? So I want to have some protons with certain velocity, and then I'm going to use these protons to do experiment. But how do you generate protons with the speed you want, right? Because you can't just grab a proton and then accelerate it, right? You have to do experiment. And even if you do experiment with these fundamental particles, usually you get a lot of fundamental particles, okay? So, and then if you want these particles to be at a certain speed, what do? Okay? So that's when we use this velocity selector, which is very important application of this theory. So let's take a look at this velocity selector. All right, so a velocity selector is a device where there are two fields set up in the same region. Both the magnetic field and electric field, they're set up in the velocity selector. And that's going to help you select the particles with the same speed, with a certain speed you want. Okay, let's see how it works. So in this on this slide, let's say the magnetic field, the electric field is created by two parallel plates, right? We already know that. That's how we create an electric field, a magnetic field. No, electric field. I'm confusing myself. Sorry. So if you charge this plate with positive charge and the other plate with negative charge, so that's going to be the direction of electric field, right, to the left, okay? So that's what we already know. Now, if I also set up magnetic field in the same region, okay, so there's also a magnetic field in this region, into the page. So how do we set up this magnetic field? Well, the easiest way is that you just grab two big magnets, right? So if I want the magnetic field into the page, so I would just place a magnet here with the north pole on this side, right? And another magnet here with the south pole facing this north pole. They're still complete magnets, right? Because remember, you can't grab two isolated north and south pole. But I can have two magnets here, and this north pole is facing this south pole, so the magnetic field is in this direction, okay? So that's how we set up this magnetic field into the page, right? Now, now imagine there's a charge coming in, okay? There's a charge coming in. Let's say this charged particle is positive, okay? So this charged particle is positive. It comes in with some velocity. So let's see what's going to happen. Well, okay, in this region, there's a magnetic field, there's an electric field. So it's going to feel two forces. Remember, this charge is moving. But in this region, there's a magnetic field, there's an electric field. Each field is going to have a force on it, right? Let's first take a look at the electric field, okay? So electric force is easy. So say it's here, then it wants to move straight down. What is the direction of the electric force on it? Well, electric force, the theory we have learned that take a look at the direction of electric field. Take a look at the sign of the charge, right? It's going to be either the same or opposite to that field. Now, this is a positive charge. Electric field is to the left. So, okay, it's going to feel a force to the left. That's going to be the electric force, right? That's going to be the electric force. Now, what about the, and that's not going to change, right? That's not going to change. What about the magnetic force on it? Then you're going to use right-hand rule, right? Because in the same region, there's a magnetic field into the page. How do you find the magnetic force? Use your right hand, put your forefinger in direction V. So it wants to move in that direction. Now curl them into B. B is into the page, right? Okay, my thumb is in this direction. So I'm going to draw the force in this direction. Okay, so you can see that at this point, if the charge is moving down with this velocity, it will feel two forces, electric force to the left, magnetic force to the right, okay? Well, if you replace this with a negative charge, then these two forces, they're just gonna, both of them are gonna flip directions, so they're still gonna be opposite to each other. Now you can see that if this guy, so this guy is gonna move under these two forces. So how does this guy move? Well, it totally depends on the relation between these two forces, right? Say, I'm going to erase this. So this guy feels to, now I'm going to redraw it. Feels the electric force to the right, feels the magnetic force to the, feels the electric force to the left, feels the magnetic force to the right. Now how does it move? Well, it totally depends on these two forces, right? Say, if the electric force is greater than the magnetic force, so then this guy's going to pull that way. So imagine, like, right, there are two forces pulling this charge, but this guy wins. So this guy's going to move that way, right? So the charge is going to be moved this way. So it's going to hit that plate, the left plate. So it's not going to go through this region. And then if the electric force is less than the magnetic force, say, right? Because all these are variables. You don't know which one is larger, which one is smaller, right? So in this case, then this force is going to win. Then that charge is going to be pulled in that direction, right? So, and then this charge is going to be moving this way. So it's going to hit the plate on the right. So still, it's not going to make it through this region, right? So, but there might be some charges, if there are like a lot of charges coming in, right? A lot of charged particles coming into this region. Say there are some lucky charged particles. When you calculate these two numbers, and they're exactly the same. If they're exactly the same, what is the net force on it? 0. If the net force is on it is 0, how does it move? It's going to keep moving in a straight line with a constant velocity, Newton's laws, right? So that means this guy is going to just move straight with the same velocity, like nothing's on it, right? It doesn't feel anything on it. So this guy, because these lucky particles, because these two forces are equal, so this guy is just going to keep moving as if nothing's on it, and then go through this region, okay? And then you can actually find out these particles, they must have the same velocity in order to pass through this region without any deflection, because you want these two forces to be equal on these particles, right? And then you can use the theory for the electric force and magnetic force, so you can find the expression for the V. So now let's do that. Okay, so I'm focusing on these lucky particles, okay? They are equal, so these two forces are equal, so they can pass this region without deflection. Now I'm going to write down these two expressions. This guy, right, this is how you find the magnitude of the electric force. Magnitude of charge times magnitude of electric field. This guy, Q, V, B, sine theta angle. What is the angle? Well, okay, the velocity is down. I'm only interested in these lucky particles. They move down, and the magnetic field into the page, sine 90, okay? Sine 90 is 1, right? So you see that these cancels this. And then if you rearrange this equation, you will get this. Okay? And remember, this is electric field and magnetic field. They're set up by the whoever is doing the experiment. Let's say you're doing the experiment. You set up these two fields, right? So they're going to be constant. They don't depend on the charge coming in, right? So that means if there are some lucky particles and then they can pass through this region without like going to the left, hit this plate, or going to the right, hit that plate, some particles, some lucky particles, they go through this region without any deflection, they must have this velocity, right? Because the two forces must be equal on these lucky particles so that they can go through this region without any deflection, okay? So you see that if you have another device to collect any particles after this velocity selector, you will always get the particles with this speed, right? And then you can tune these two fields, right? Because you set up this velocity selector. You can say, I want these particles to be, I want some particles with 5, 10 to the 5th meters per second, and then I want these particles to do some experiment. How do I get these particles at exactly 5 times 10 to the 5th meters per second? Well, set up a velocity selector, and then fine-tune these two numbers, right? Because you're going to set up an electric field. You're going to set up the magnetic field, right? So dial these dials until these two numbers, the ratio between these two numbers is exactly 5 times 10 to the 5th meters per second. Okay? Then you can do an experiment, and then you can generate all kinds of particles, right? Let them go into this velocity selector. Some particles is going to be going in that direction, okay? Some particles will go this direction. They are going to hit these two plates. You're not going to see them. All you need to do is just wait here, collect particles here. So all these lucky particles, they pass through this region. They will have this velocity you need, right? So they can still be different particles, but they all have the same velocity. So that's why we call this velocity selector. Okay, it's going to select the particles with a certain speed you want. They can still be different particles, right? Because you see that the charge cancel, okay, and it doesn't have any mass in it. So you may still have a lot of particles, but all these particles you collect after this velocity selector, they will have the same velocity. And then what is that velocity? Well, you tune these two fields. You can always get the particles with the speed you want. That's why it's called a velocity selector. Okay? I'm going to stop here.